Hi everyone, and welcome to the section 5.6 video. This one is called integration by parts. So we're just on to a new method for trying to do integration. All right, we just did substitution, so hopefully that's feeling a little bit better practicing that. This next one is called integration by parts. And so we're just going to kind of very briefly go through the thinking of this. It's really not too bad to kind of see where the formula comes from, right? And so you can kind of go through here if you want to and check this out. And it's all based on the product rule for taking a derivative. So hopefully you continue to see this interplay between doing derivatives, antiderivatives. Taking derivatives, trying to solve integrals. It's just these, back and forth between them. So, I think that when this first was thought of, someone was looking at this integral right here, and they were saying, darn, I know how to do this sine 2t. They're like, I know how to do this antiderivative. I know how to do this one, right? Separate them, I'm great. And so maybe they thought something like, man, if I could only make one of these simpler so I could get to just this one. Oh, the t, well, if I take the derivative of this, that's just 1, right? So if I do the derivative of just t, I get 1. So is there any way for me to think of doing derivatives where I can get the situation where I've got these two functions and I take the derivative of one but still have the other? And then maybe at that point they thought, oh wait, I remember a formula that involves functions multiplied, one kind of regular, one took the derivative. And that's where this function comes in. And this is where the heart of this is. Recognizing that you have two functions to start, not always so obvious, but you've got two functions to start here. And it's like, oh, I can see them separately, and I can do derivatives, antiderivatives of them. I can think through that, right? But the key point that you're often going to see is one of these functions gets much simpler, much easier if I took the derivative. And this formula here can help me turn this integral into one where I only actually have the derivative instead of this t. That's the goal of integration by parts, is to look at these two and be like, I could do them separately, or I could do them if I could simplify one. That's what integration by parts lets us do. It lets us pick out a specific function here, and it's going to be this one, t, and say, I can simplify that using a derivative. Now, sine, this doesn't simplify, right? Sine goes to cosine, goes to sine, they just keep bouncing. So this is not simplified by doing a derivative, but it's not harder doing an antiderivative. Sine and cosine just bounce, right? So what you're often going to be doing here is, and there's two things you're going to pick out, and I'll give you the formula in just a second, okay? So there's two things you're going to be able to pick out here. And one of them is you're going to look for a function in here and going to go, oh, can I do its derivative? Does it make it easier? Okay, so the one of these things you're looking at is there a function that if I do the derivative, it gets easier? This is not the only way you do integration by parts, but it's often pretty good. And then you're also looking for a different function. All right, so this one is different, where if I do the antiderivative, either it gets easier, which is nice, or it doesn't need to get easier, but maybe about stays the same. So it doesn't get a lot harder in terms of doing derivatives, antiderivatives, okay? And that's, I know this sounds weird, but that's our kind of goal. Pick out a function, take the derivative, it got easier. Pick out a function, if I do the antiderivative of that, it about stays the same. So what is this method? Well, go through here if you want to kind of see it done out. Just use a little bit of algebra plus this rule. But the method is actually this. We are going to take an integral. We're going to identify two functions, f is going to be one of our functions. So here's the integral we just looked at. T sine 2t, which is going to be our first example. So we're going to identify an f and then an g prime. I know that's weird. What do you mean g prime? You'll see in a second. We're going to identify these two, and then this formula tells us that this integral is equal to, well, f times, this is g prime. I need to take the antiderivative of g. Remember when I had said, hopefully this function doesn't get worse, harder, difficult, whatever, if I do the antiderivative? That's because it's right here in the formula, the antiderivative. So I just have to do the antiderivative of this function. That'll go right here. So we'll do that in a second. Minus the integral of the antiderivative of this. We'll do that in a second. Times the derivative of f. Oh, but that was just 1, right? Look what happened. I simplified t down to 1, which is going to make this integral way easier to do. So it's a silly little trick where you've got something in here, can't quite do this. You can replace this integral with this one, where you've taken t and simplified it by doing the derivative. Now, you've replaced g prime with g, but hopefully you didn't make things worse for yourself by doing the antiderivative. And we'll see that in a second. So let's do that one real quick. If g prime of x is sine 2t, then we have to do the antiderivative, okay? Now, we gotta be a little careful here because this is not just sine 2t. So to do the antiderivative of here, guess what we need to use? We have to do substitution. So we're going to do that here, and I'll change the color so we've kind of got this separated a little bit. So to actually do this, we're going to have to do u equals 2t, du equals 2 dt. Okay, so that's du over 2 equals dt. Remembering our rules from 5.5. Okay, so once we have that, we now have sine of u, right? So we're actually just doing this integral, sine of u du over 2. This one's not too bad though, right? It's negative cosine u over 2. And then what do we have to do, right? We have to go back to t's, which gives me negative cosine 2t over 2. So that's going to be our g of x. So this just gets plugged into our formula here and then in here. I ran out of room. That's why I'm writing g of x there. So negative cosine 2t over 2. And this maybe is like, you're looking at this like, oh, that's still kind of complicated, but it's way, way better than this one, right? You got to agree with that. This, once we've got the negative and 2 out of here, get rid of that 1, this integral is much better than this one. And that's the point, okay? So this is a kind of idea of what we're going to do here. Now, this formula might be a lot to remember. Often you're going to see this formula written in a different way, where we get rid of f of x and g of x and g prime, and we have a little substitution we do here just to make it easier sounding. So we say, let u be f and v be g, okay? And then this becomes the integral of u dv equals uv minus the integral of v du. This is what you need to remember. So let me mark this. To remember, you have to remember this formula, and you have to remember, so you got to remember this, and you have to remember that you are going to be, at the start of each of these problems, picking out u and dv. So you're going to take your integral, and we'll practice this a ton, because I know this is a little weird sounding possibly. We're going to pick out a function and call it u, pick out a function and call it dv, and then we need to remember uv minus the integral of v du. uv minus the integral of v du. Just say it to yourself. uv minus the integral of v du. Say it to yourself enough so that's in your head. But that's it. We pick out which function is which, we remember this formula, and we go. All right? So these are the things to remember. This is the process we're going to do. So let's get into it. Let's try it. Let's just try a bunch of them to see what happens. Okay, so this first one we actually kind of started, but I want to do it using, the kind of standard method since we just played around with it a little bit. So here is the method. What did we say? Pick out a u, pick out a dv, and then over here we have to remember uv minus the integral of v du. Okay, so again, we need to pick out a function u that gets easier when we take the derivative. You might be like, wait, why? Why do we care about that, right? Well, look over here. Du is in the integral. I don't want to do a difficult antiderivative, a difficult integral, right? So I want du to be simpler. So looking at these two functions, t, sine 2t, I think to myself, you know what? I'm going to pick t here because the derivative of this is 1 dt, and that can't get any easier. So I know that over here, it's just going to be 1. Okay, awesome. That's a lot better. All right, well, that forces dv to be sine 2t, and we just did the antiderivative of this, right? It was negative cosine 2t over 2. So pick out u and dv from here. Then we do these calculations. Then we plug all of this into our formula. So I'm going to do that here. Ready? U, V, and we'll simplify this and move stuff around a little bit later, minus the integral of V du. uv minus the integral of v du. Okay, so let's simplify down a little, move some stuff to make it nicer. So this is negative 1/2 t cos 2t. Two negatives makes a positive. Take the 1/2 out, cosine 2t dt. All right, this integral is equal to that, which is equal to that. Now, we just did a whole process and didn't solve the problem yet. But look at this integral. Way, way better to solve than this one, right? We've put it into a form that we can solve. So let's try doing it. So over here, and it's totally fine to do something like this. You just got to keep yourself organized. We're going to work on this kind of separately, and then we'll bring this back in after, okay? So remember, cosine t? No, it's cosine 2t. You got to do a u sub. du equals 2 dt. Bring it over. Okay, so this is going to give us the integral, got the 1/2 still, of cosine u du over 2. Okay, what's this one? Antiderivative of cosine is sine. 1/4, because the 2 and the 2. Sine u plus c. Okay, and then your u gets replaced with 2t. 2t plus c. Okay, now that was just that piece, right? So we got to bring it all together. So let's bring it all together. So we've got equals negative 1/2 t cosine 2t plus 1/4 sine 2t plus c. And there we go. So let's do a little recap. Pick a function u that gets better when you do the derivative. Pick a function, which is usually whatever's left, dv, that doesn't get too much worse when you do the antiderivative, which goes here. Okay, set things up. You have a simpler integral now. Do it. Put it all back together. Let's try another one. Okay, with this one, Similar thing, I see two functions. Okay, so let's go at this. We have to pick out a u and a dv. All right, and then we have to calculate du and v. And then what do we have to remember? This is equal to uv minus the integral of v du. All right, we've got it all set up. So this one is a little tricky because it still kind of follows the idea that we had before, but your intuition using the idea that we said before might be a little off. So there's two options here for you, p to the fifth or natural log of p. Here's the best thing about this. You could just try something, do it out, put it down here, and if you get an integral you can't do, well, you try something else. And there's usually only two options, so go try the other one. So what if we tried this? This is our first try. What if we tried this? Well, the derivative here is not too bad, 5p to the fourth. But we got to do the antiderivative here. I mean, we can do this antiderivative, right? But it's not very nice. And actually, we haven't seen how to do it yet in this class. This is actually in this section. So you can get to this point and get stuck. So once you get stuck, try something else. So, okay, we got stuck. Let's try something else. All right, so instead we choose natural log here, which leaves p to the fifth here. Okay, so derivative of natural log is 1 over p. The antiderivative of this, oh, that's not too bad, right? It doesn't get crazy. Just p to the sixth. Okay, so this isn't too crazy. So let's just see what happens. So uv, so 1/6 natural log of p times p to the sixth, that's uv, minus the integral of v du. Now hopefully you're starting to see, oh, this was a pretty nice fit together, because what happens with these two? P to the sixth and 1 over p, oh, those can combine, right? So again, we're just going to do this one separately. We're going to kind of do this out on its own. This is really 1/6 integral. Okay, I have 6 p's on top, 1 on bottom, so that leaves me 5. And wow, look, that's simplified like crazy. I know how to do this. I actually already did this one, right? We've already did this. So don't think too much. If you've already done something like this, just redo it. So this is 1/6 times 1/6 p to the sixth plus c. Okay, so let's put it back all together now. Don't forget to do that. We've got all together, this is equal to 1 over 6 natural log of p times p to the sixth. And then we have minus 1 over 36 p to the sixth plus c. And we're done. Woohoo! All right. We picked a u, we picked a dv. We had messed up the first time, but that's okay. We tried a new one, did the calculations, plugged into our formula, do a little simplifying, usually algebraic, solve. Integration by parts. All right, so let's try a new one. So this one's another one that's a little bit different, right? So we're sitting here, and we might be looking at this like, oh, geez. Well, kind of, we're broken down here a little bit because I don't even see, I don't see a second function, right? Well, there's a common trick whenever you're in a situation like this. Anytime you're in a situation where something calls for 2 of something, or maybe even 3, or however it is, and you don't have enough, well, one nice trick is that there are 2 functions here. If you look really hard, let me show you where they are. Here's one. Here's the other. You didn't see that first function there the first time? Well, there it is. Okay, so once we've got this, now we've got 2 functions, and then we have to think, okay, well, what can I pick here? Well, if you tried to just jam u as 1, you're going to do du and get 0, and it's going to mess everything up. Because remember, it's uv minus the integral of v du. Du being 0 is no good, because then this whole thing's 0. That's not going to work. So let's try this, where we put 1 here, okay, 1 dx, and then we put sine inverse here. And you know, some of this comes down to remembering, having that toolbox be full for your derivatives, because it's a lot harder to do these problems if you don't remember that you can do derivatives of some of these functions. If you're looking at sine inverse and you're like, no way, in no form or shape am I doing anything with this, that's going to really hurt you in being able to do this. But if you look at sine inverse and you're like, oh man, I don't know how to do the antiderivative, but I do have this in my toolbox for the derivative, well then you can be pretty comfortable that picking this as you. 3, 2, 1. So if we dig deep into our toolbox, we can remember that this is 1 over the square root of 1 minus x squared. All right, so again, maybe we had to dig kind of deep into our toolbox there, but we've got it. So then, okay, what's the antiderivative of 1? Well, it's just x. All right, so you might be looking at this kind of like, this does not look better. Well, just give it a shot. Try plugging it in. So we've got uv, okay, minus the integral of v du. So I'm just squishing them together. Okay. So let's look at this. We're just going to focus on this integral now. Is this something that we can do? So look at it, look at it. Remember, everything is on the table here. Every method, everything you have. So, do I have to do this integration by parts thing again? No. Wait, I think I see a function and its derivative. I think I see a function inside another function. I do. Haha. This is just substitution. Right? I've got an x dx. Excellent. So get this negative 2 over. Okay, and then we're going to do the substitution. So we'll do it right here. So this integral is actually the integral, and then remember, x dx becomes du over negative 2. So this ends up being 1 over the square root of u du over negative 2. Okay, so I'm going to take that out. Integral, and then remember, we got it, just algebra's got to be quick with this, right? 1 over the square root of u, that's the same thing as u to the negative 1/2. So it's a good form to do the antiderivative of. Okay, so then let's do the antiderivative. Add 1 and divide. So we add 1, we get 1/2. We divide, that's times 2. U to the 1/2 plus c. Okie dokie. And then we can do a little simplification here. This just becomes negative. And then, you know, you can go quick here if you want. No more u's. 1 minus x squared to the 1/2 plus c. And then let's bring it all together. All right, let's put it all together. We end up with, this is equal to x sine inverse x minus becomes plus 1 minus x squared to the 1/2 plus c. Boom. So that one started kind of crazy, right? There's not even 2 functions. Of course there is. There's 1. And wait, this didn't get, you know, simpler or stay the same. This got harder. Well, that's okay, because it gave us that extra x here in order to use substitution. So hopefully not too bad. We now know the antiderivative of sine inverse x right here. All right, let's keep going. Okay, so let's look at this one. So this one is pretty tricky. Okay, this one's tricky because it pretty much breaks all of that intuition kind of setup that we had. Because you might be looking at this and think, wait, both functions here do not get simpler. They just kind of do the same thing over and over, right? take the derivative or the antiderivative of either function, and you're just going to keep getting the same thing, right? Sine goes to cosine, goes to sine, goes to cosine. E goes to E, goes to E, goes to E. So this is one of the ones where, this is beyond anything I would give you on a test or anything like this, but it's one of the ones where you've got to really trust yourself. So let's just watch what happens here. So u equals dv equals, okay, so I'm going to pick u here, and then before we do that, so that you have this context, let's write this down. uv minus the integral of v du. Okay, I'm going to pick sine here, and you're going to see why I do that in just a second. So then that leaves this as my dv. Okay, so let's do our derivative. So the derivative of sine is cosine, but remember this is technically chain rule, so we get that 3 that pops out. Do the antiderivative here. Now I'm going to do this one quick, and this is something that is a nice pattern that you guys can pick up on. Anytime you're doing the antiderivative of a function, and the only difference between that function and a very simple regular old function is a number multiplied in here against the variable, then the antiderivative will just be, take the antiderivative like you would of this simpler function, right? And then pop out a 1 over that number. So good practice, do substitution here. But what you're going to end up getting is that this 2 ends up just kind of just boop, popping out down here. All right, so let's plug this in and see what happens. So we get uv, so that's 1/2 e to the 2 theta sine 3 theta minus the integral of v du, 1/2 e to the 2 theta, and then du, remember, is this 3 cosine, 3 theta. Okay, so we're at this point now. We have not made this easier. We've just switched to cosine. But what we hopefully can see is that if we do this process again, we're going to get ourselves back to sine here. Okay, it'll still be an e and then something with sine. But remember what we're doing here. This is equal to uv minus the integral of v du. If we can make this somehow into a copy of this, we're going to have an equation where we can solve for this. This I know is crazy sounding, and I'm just going to show you how it works. But it's a very neat trick that at some point in the future, thinking this way, of it not being so bad to kind of cycle, you might be able to do this trick in the future somewhere in some way. Might not even see relevant, but it'll be in your head. We're going to cycle back to this and then solve for it. It's a little crazy, but just watch what happens. So let's clean this up a little bit. The 3 and the 1/2 can combine. So we end up with 1/2 e to the 2 theta sine 3 theta minus 3/2 integral e to the 2 theta cos 3 theta d theta. Now we're going to do out this integral. Just right here, we're going to focus on this one. Okay, we're going to do the same process. U equals cos 3 theta. Okay, du, and then we've got dv equals e 2 theta, v equals. All right, derivative. Derivative of cosine is negative sine, but this is technically chain rule, so don't forget your 3. Well, we already did this antiderivative, so that's not too bad. E to the 2 theta. Okay. All right, so let's put this together again using your integration by parts. So this would be uv, right? So that's, and then we've got our u, minus the integral of v du. And then we've got our negative 3 sine 3 theta. All right, let's clean this up a little bit. 1/2 e to the 2 theta cosine 3 theta. And then we can put these two together and bring it out. That's a plus 3/2 e to the 2 theta sine 3 theta d theta. And then what did I say was going to happen, right? This integral right here is this one, e to the 2 theta sine 3 theta, e to the 2 theta sine 3 theta. So we're able to cycle back to our original. Now, you might look at that and be like, oh, great. So watch what we get to do here. So I'm going to have to write a little bit smaller to fit this all on one line. But watch what happens. So this is what is in the green here, right? And so we've got to, we got to put this all together and simplify a little bit. So we're going to do that. So this, remember, is 1/2 e to the 2 theta sine 3 theta, right? And then it was minus 3/2 the green. So the 3/2 comes in here, right? So it'd be minus 3/4 this first piece. And then the minus travels in over here. Remember, that's this minus 3/2 travels in here. So it'd be minus 9. And then the half, again, is coming in here, 4ths. And then we've got the integral e to the 2 theta sine 3 theta d theta. Okay. So here is the tricky thing. What is this equal to? Right? What is this thing? Well, it's equal to our original integral, because that's what we started with. But look, I've got the same thing on both sides. So what you could do, if this is a little tough for you to see, is just take this whole thing and replace it with an x. Okay, so let's rewrite what we have. 1/2 e to the 2 theta sine 3 theta minus 3/4 e to the 2 theta cosine 3 theta minus 9/4 x equals x. We want x though, right? That was the whole point, is finding this integral. What is it? So solve for x. Move this over. You're going to end up with plus 9/4 here, right? So that's going to be 13/4 x. When I move this over, add it over, and then I have this here still hanging out, sine 3 theta minus 3/4 e to the 2 theta cosine 3 theta. Okay, now again, solve for x. Move this over, and we end up getting 4/13 times 1/2 e to the 2 theta sine 3 theta minus 3/4 e to the 2 theta cosine 3 theta. Plus c equals, and then what was our x? Well, it was just our original integral. E to the 2 theta sine 3 theta d theta. Boom. Again, a little crazy for a test, but just an interesting problem where you can see that even though this doesn't follow our intuition that we're trying to build of u as a simpler function so that we can make this simpler, it's still a useful trick in situations like this, even when it isn't immediately clear how this is helpful. So just a nice tricky one for us. All right, so then we have to do some examples where we have definite integrals. But this is very similar to a u sub where you can just, for the most part, ignore it while you're trying to do the actual integral. So let's go ahead and, basically just ignore the bounds for now and still set up what we do. U equals dv equals du v uv minus the integral of v du. Okay, so something that gets simpler when I take the derivative, something that doesn't change much. U equals, let's try x squared plus 1, so 2x dx. That leaves me with this as the only choice for dv. And then, if you're following that trick I said before, I have a negative 1 up here. It's the only difference between this and e to the x. So that just pops out on the bottom here. And there you go. It's a pretty easy antiderivative to do, but again is technically using substitution. So okay, let's plug into our equation. So this is going to be negative e to the negative x times x squared plus 1 minus the integral of negative e to the negative x times 2x dx. Now, you're going to look at this and be like, wait, this isn't just like easy and I'm all done. True, but it did get easier, right? I had an x squared here before. Now all I have is a 2x. That's simpler. So, okay, that's getting better. Now, what about the bounds? The bounds just come along. So we want to evaluate this from 0 to 1. So you're just going to keep the bounds along the entire time. That's it. That's all you have to do with the bounds. It's not too bad. Just don't forget them. So let's simplify this a little bit. Negative e to the negative x. And you can actually do the bounds all at once later, but I just want you to not forget about them. That's why I'm putting them here. 0 to 1 minus, and then 2 in the negative. This becomes a positive. Bring the 2 out. Integral 0 to 1 x e to the negative x dx. Okay? So then let's just do our integration by parts again. U equals x. dv is e to the negative x. Okay, du is 1 dx. V is negative e to the negative x. All right, I know I'm doing some of that quick, but we already did this one. So that's why I'm doing it quick, because we already did this one. Okay, so again, I'm just focusing on this right now. All right, so uv minus the integral of v du. Okay, and hey, we got to something pretty nice, right? So don't forget, we're doing 0 to 1, 0 to 1. Okay, minuses cancel to a plus. And for the third time in this problem, we are going to be doing this antiderivative. Don't forget your 0 to 1. So that's negative x e to the negative x. Okay, do the antiderivative. Minus e to the negative x. And like I said, we can just do this whole thing 0 to 1. So let's bring down everything else. What did we have still? We had e to the negative x times x squared plus 1. So let's bring that down. Negative e to the negative x times x squared plus 1. Okay. And then there was still the plus 2 times this. And we can do all of this from 0 to 1 just at the end here, which is pretty nice. You don't have to do it separately. It hits every piece, but you can just do all of this together at the end and plug in the bounds, which is pretty nice. So let's plug the 1 in, and then we'll plug the 0 in. So the 1 goes in, negative e to the negative 1 times 2 plus 2. And then we plug 1 in here. We're going to get e to the negative 1 minus e to the negative 1, right? So that's minus 2e to the negative 1. Okay, so then we're going to do big minus, and now we plug 0 in. All right, so plug 0 into this, you get negative e to the 0. This becomes 0, so that's just times 1, which is, you leave it, plus 2, and then this becomes 0 because of the 0. Negative e to the negative 0. Keep simplifying. Okay, so we just have a bunch of copies basically of e to the negative 1 over here. So that's negative 2 copies minus 4 copies is negative 6 copies of e to the negative 1. And then over here, remember, e to the 0 is just 1. So we end up with this becomes 1, and then this becomes -1 right here. This becomes -1. That becomes 1. So what does this end up being? This is minus, okay, and then we've got 1 minus 2, which is just a -1, so plus 1. There you go. So hopefully not too bad to do that. You can basically just treat it like a regular problem without bounds. The bounds travel along, and you can just right at the end apply them. Okay, I believe this is the last one. Yep, so last one here. Let's try it out. U equals du equals, and then we've got dv and v. Okay, so what are we going to pick here? Well, we saw natural log earlier and really did not want to put it down here. So just because of previous experience, I don't want to put the natural log here. Let's put it here. So that gives me 1 over y dy. That leaves 1 over square root y as my dv. But remember, this is y to the -1/2. Okay. Do the antiderivative. Add 1, divide. So v is going to be equal to y to the 1/2, and then divide 1/2, that's 2. Okay. So what's our formula? uv minus the integral of e du. Okay, let's try doing it. U and v. So this is 2y to the 1/2 natural log y, okie dokie, minus the integral of 2y to the 1/2, and then what's du? 1 over y dy. Oh, nice. We're in that situation again where we just have powers of y that'll come together. So that's pretty good. Now don't forget, we still have these bounds, but we'll just apply them at the end. All right, let's clean this up. 2y to the 1/2 ln y minus, take the 2 out, 2 integral, and then I have half a y on top. I've got a full y on bottom, so that's 1 over y to the 1/2 dy. Okay, so then just kind of doing this off to the side a little bit. This right here is really the integral of y to the -1/2 dy. Okay, add 1, divide. We already did this one though, don't forget. What are you doing, extra line? Okay, so then let's put it all together. 2y to the 1/2 ln y minus, so 2 times this, 4y to the 1/2, and then we've got to do all of this from 4 to 9. 4 to 9, okay. Plug in the 9. That's going to give me 2 times 9 to the 1/2 is 3, so that's 6 natural log of 9 minus 4 times 3 is 12. Now let's plug in 4. 4 goes in here. That's 4 natural log of 4 minus 4, and then plug the 4 in, that's 2, so that's 8. Doing some quick mental math there. Putting this together, this will be 6 natural log of 9 minus 4 natural log 4 minus 4. There you go. So I knew I'd do the algebra kind of quick, but you can always pause and do it out yourself, right? So you could even slow me down. So it's like 2 9 to the 1/2. I did that, not you. Don't check the settings. But you can slow me down too on the algebra. Okay, there you go. So lots of different types of problems here for you to see kind of what this looks like. But hopefully one of the things you're getting is you got to remember just the setup, and then you have to just do a bunch of these to build your intuition. Like this last one, I had a really good feeling u was going to be a natural log y because we did a problem before where natural log fit better as the u and really was not good as the dv. So now you can do another problem. You see natural log and you should think like, oh, I bet that's probably just going to be u. Let me try that first. And you got a good shot of it working. So, you know, again, some of these were a little tougher than what I would ask you to do on any kind of test or anything like that. But you can see that it's a piece of the puzzle. Sometimes you use it and then you have to use another method, right? Sometimes it's an integral you're going to get that's real easy to do. Awesome. Sometimes you got to use substitution after. Sometimes you might even have to do integration by parts again. So practice up, practice, 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 and let me know if you have any questions. I'll see you in the next video.